Alright, this video we're going to be looking at the UART, or the Universal Asynchronous Receiver Transmitter, which for microcontrollers is TTL RS232. Alright, so we're working at somewhere between 0 to 3.3 or maybe 5 volts, but using RS232 as the protocol. Note, sometimes you might see the word synchronous in here. Some microcontrollers actually allow you to run a synchronous UART, but we're going to ignore that for now. We're going to refer to it just as the UART. Alright, so a UART basically looks like this. You've got your microcontroller, got a couple of pins, one will be TX, one will be RX, and you'll have another device. Alright, it might be a GPS unit, or it might even be an LCD, it could be lots of different peripherals, but we have some sort of device here, some external peripheral, and it too is going to have RX and TX pins. Now note my connection here, guys. Lots of people get this mistake and it's very costly on a PCB. TX from the microcontroller connects to RX of the device, and TX of the device connects to RX of the microcontroller. TX does not go to TX. This guy will be sending things which will crash into this guy's TX. Alright, so a couple of lines. It's known as 3-line because generally we also have ground between it as well. But on a circuit board we ignore that. We've only got 2 lines basically. It's asynchronous, this word here, because we have 2 clocks. There is no shared clock line between these. So you have to make sure that the speed and the format of your transmitter matches the speed and the format of your receiver. And remembering they can swap roles. Right, this can become the TX and this can become the RX. Alright, so the speed and the format. And we're going to talk about these two things as we go. Nice things about the UART is it is very simple. Right, 2 wires. It is full duplex, which means we can transfer information in both directions simultaneously, which is quite an advantage. And as far as all communication interfaces go, I consider this the easiest to use. The only thing that would be easier would be pulling a line up and down. Alright, so realistically this is as simple as it gets. So easiest to use is a huge advantage for the UART. Right, so how does it work? Well, because you don't have a synchronizing clock between the two of them, there are actually extra bits which are added between our along with our data. So I'm going to use blue here. I'm going to draw underneath here. These are our data bits. Alright, so this is what we will actually want to send. In order to synchronize the transmitter and receiver, because remember their clocks could be going at slightly different rates or it could be out of phase with each other, we have 2 synchronization bits, normally 2, sometimes 3. We have a start bit and 1 or 2 stop bits. And from those, 2 different devices running at approximately the same clock rate, but with probably different phases, can synchronize themselves to be able to receive the data. As well as that, we have some basic error detection via what's known as parity, which we're going to talk about shortly. But that's realistically all there is to serial. All of this is generated by hardware, so start bits done by hardware, stop bits by hardware, and the parity bit by hardware. All you have to know what to do is what data you want to send, which is what makes it so nice. All that stuff is added in by hardware, done by hardware for you, and you just read the data back out again. So it is really easy. Things to worry about, right, it is optional, these bits here. Okay, generally 8 data bits. Okay, 1 byte makes more sense, it's easier to work with, but you can have 5, 6, 7, 8 or 9 data bits. They all are fine as well. 1 or 2 stop bits. In fact, because we're doing generally, I'm going to say 1 stop bit, the number of synchronization bits here at the end of our packet of information. Generally it's 1, and generally it is no parity. And we abbreviate this into a format, 8N1. It's the same as 8 data bits, no parity, 1 stop bit. Right? And we could have other ones, 5, even, 2, for example. 5 data bits, even parity, 2 stop bits. Okay, that's the unusual one. But we have these little strings that you should be familiar with when you're reading data sheets, which tell us a bit of information about the format. Remember, this is the format here that I'm talking about. Before we get on to speed, let's just quickly look at parity. So this bit here is our error detection bit. And the parity bit, as it says here, exclusive OR of all the data bits. If odd parity is used, the result of the exclusive OR is inverted. Right, so it's an exclusive OR between all of these. And whatever the data is, that's calculated. That bit is placed in here, and it is sent along with our data. The receiver, so parity is calculated by the transmitter, sent with the frame. Frame, as we're saying up here, is all of this data, including the synchronization and the parity. Sent with the frame. Receiver calculates parity again, and compares. If same 0 or 1 is calculated, okay, maybe. Parity is an error detection which only works if 1 bit is corrupted during the transfer. If 2 bits are corrupted or flipped, then it's not going to work, or any multiples of such. So it's not very robust, and to be honest, I don't normally use it. In fact, you have to manually check that flag. You'll still receive information from your serial port even if it says it's been corrupted. So not normally used. There are more robust strategies involving CRCs and so forth, which allow you to correct, or with Hamming codes. Okay, so parity is a very, very rough way of detecting error. Detection, not correcting. And only 1 bit. That's the real downfall to it. So that's parity. So, which is why generally no parity, 8N1. We also have the speed at which our transmitter and receiver are operating, which is to do with the clocks here. Speed with respect to UARTs is known as baud rate, which is sometimes known in bits per second as the calculation. Alright, so baud rate between the transmitter and receiver must be the same speed. Make sense? Right? So we put that all together, so we have things like 9600 8N1 equals 9600 baud, 8 data bits, no parity, 1 stop bit. And that's a very common format to be started with, and speed. Right? It's a really nice one. I suggest you use it. If you need to go faster, there are other common ones which we're going to look at later on, but that's one of the slowest, easiest ones to work with. Slow is good, it avoids errors. Right? The only problem, or transmission errors, the only reason you go any faster is if you've got data rate problems. You need to send more data. Right, so that's the UART basically. 2 wires, 1 transmits, 1 receives. Those can obviously flip around depending on who's sending to what, but it is full duplex. It's very, very easy to use. Remember these strings, these are quite common, 9600 8N1. Okay, remember parity, what it is, but we don't normally use it. 1 stop bit, 8 data bits, because we use 1 byte. Alright, let's see how we would set up a UART. There is a number of registers, normally about 3 associated in a microcontroller, and they come down with a whole lot of options because they're actually quite flexible. So what we're going to have a look at here, we've got a couple of interrupt enable flags within the BUCSRNB register. We're not going to start with A because we're going to get to that shortly. The one that I would normally use is not this one, but this one, the RX Complete enable, because that one I can set up that every time I receive a byte over the serial port, I automatically get an interrupt associated with it. Alright, that's quite useful rather than checking status flags manually. And that's one I suggest you use once you get into serial ports a bit more. For now, we're just going to forget about interrupts, but just remember that this one is useful. Okay, so no, we don't want interrupts on any of those pins there. Normally, you're going to want to enable the receiver and transmitter. Okay, sometimes not. We've got a character size bit we're going to look at shortly, and then if you are using this oddball 9-bit serial port, then these are your 9 bits here. Okay, so they actually sit in this register. Normally, I don't like anything to do with those. Keep things easy as a 8-bit or 1 byte. So really, you want to enable RX and TX and set the character size. That's all you want to do with this register. So it's actually pretty easy there. We can ignore most of it. Within register C, right, we've got the UART mode. Normally, we're going to operate in asynchronous. Right, synchronous, like I said, exists, but we don't normally use it. So because they're 0, 0, okay, leave those as zeros, that's fine. Parity mode, normally, like I said, it's disabled, so I don't need to worry about those. Stop bit, normally is 1 bit, so once again, cross off that guy. So you can see this is nice and easy to set up. And then the only ones we've got to worry about are the last 3, character size, which we actually do have to set up here. And clock polarity, only used for synchronous, so we can cross that off. Right, so we only have to worry about those 2. So of the registers, really all we've got to do is enable the receiver and transmitter and set up how many bits we want for our character size. And we always want 8. So, well, always generally want 8. So UCSR1C would look something like in binary 0, 0, 0, 0, 0, 1, 1, 0, where the 1, 1 comes in from these 2 here, ZN1 and ZN0, to these 2 here, and UCSR1B will equal in binary 0, 0, 0, and 0, 0, 0, and then 1, 1, 0, 0, 0. So that's RX enable, that's TX, and that bit 2, remember from this table down here, was actually a 0. Tick it off as we go, always a good idea. So they're nice and easy to set up. So that serial board is now basically ready. We've enabled transmitter to receiver, we've told it how big, we've told it the format. Okay, so format, set, and it's enabled. The last thing we need to do is, just like I said, the speed. Alright, so there is one more register, what's known as UBRRH, baud rate register, so UART baud rate register. And then this one we actually have a 16-bit register, so we actually have a high and a low. Generally, just write to UBRR1, for example, or 0 or whatever it happens to be. Don't worry about the high or low. You can write separately and work out numbers that have to go into each of those, but Atmel Studio can just work it out. When you're writing to a 16-bit register, it splits it up automatically. Alright, so generally just write to UBRR1. Don't worry about H. Don't worry about the L. But you can if you want to, if that's how you prefer to code. Now, a few things to watch out for here. Dependent on the oscillator frequency, will depend on how accurate you can generate the baud rate in bits per second. And depending on whether we use that 2 times flag, which I haven't talked about yet, but we will get to. So normally I don't. So this is normally what we're using. I ignore that. Okay, we've got 8 megahertz, so we're we are somewhere within this area of the table. Watch out, anything greater than about 3% and you can run into transmission problems, right? Because this clock rate does not divide equally into these baud rates, which are standard values, right? We can end up with a clock running here at a much significantly different rate from the guy from our receiver, our device's clock. And therefore we can end up with corrupt data transfer and all sorts of problems. So really you want to avoid any of those values which are greater than 3. So for us, 38,400 is a good one, 250k if you can get it to work, or like I say, 9,600 is pretty good. Note that this oscillator frequency seems a bit of an oddball value, 11.0592 megahertz, but all of a sudden we see, that's why maybe it's an oddball value, because it divides evenly into common baud rates. So sometimes you actually choose your crystal based on being able to get to accurate baud rates. Right? However, it does fall over here. But for us, we're not worrying about those. They're not in our applications board. We're only in this red area here. And normally I would say go here, but start here. Always start slower, and if everything's working, you can migrate to a faster speed. And you can keep going if you wanted to this one. So that's our speed. So we would do something like UBRR1 is equal to, we're going to start with 9,651, using that value there. And that's it. Our serial port is now set up. The only thing left to do is use it. So to do that, we've got another 16-bit register here, UDRN, which is actually the transmit data buffer register and the receive data buffer register. So UDR1 equals data, that's transmitting, and data equals UDR1 is receiving. Right, seems simple enough. Yes, but before we do those, we do need to make sure that the buffers are full or empty for us to be able to do them. Alright, so left hand side for TX, right hand side for receiving. So we've got one register to worry about, once again 16-bit, only because the fact it is both transmit and receive, it is actually only 8 bits. So you only receive 1 byte at a time. We come down here to our UCSRNA, which is the A register. Normally we start with A. This one in fact is actually more of a status register rather than a control register. And the bits of interest for us are receive complete and data register empty. Alright, and the rules are basically as this. Don't TX unless UDREN is equal to 1. Flag indicates if the transmit buffer is ready to receive new data. Right? If it is equal to 1, the buffer is empty. So while UCSR1A dot 5 equals 0, wait, then UDR1 equals the data. Okay? So before you can send data, you must check to see that this is empty, and don't receive unless RxCN is 1. This bit here. Alright, this flag is set when there is unread data in the receive buffer. Okay, so while UCSR1A.7 equals 0, then data equals UDR1. Now, quick hint, this one is okay for use. Alright, you want to send something, you probably don't want to be doing anything until you've actually can send it, so that one's alright to use. This one, on the other hand, not so good in practice, because it's quite common that you don't have control over when you are going to receive data. It's up to the slave device. So do you want to stall your microcontroller here, waiting to receive something, or are there better things that you can be doing? Reading inputs, for example, displaying something on an LCD, doing some calculations, servicing some other sensors. Right? So not so good in practice, which is why I suggest to use interrupts for checking for received data. Okay. Do not poll. Generally is the way to go. So set up an interrupt. I showed you that in that first register B that we looked at. Receive complete interrupt. It is useful. Don't sit there waiting for the other's device to send you something back again. Alright, you can stall your micro and stall the whole program doing that. So use an interrupt. Alright, so that's it. Register A is more of a status register. That's what we use it for, not a control register. Just remember UDR1 can be used for transmitting and receiving. And that baud rate, just remember, avoid greater than 3%. And that's it. It's really easy to use. Once you get the interrupt working, get a bit of a buffer working, it's really nice, really simple, and I've had it working quite happily, well up to, I think, 1 megabits per second without issue. So, have a go.